Okay, let's take a look at manipulating variables in Octave. We'll take a look at some of the basic mathematical operations and then also accessing elements in matrices and matrix mathematical operations. Um, so this is a little bit of a long video. Of course, Octave supports all the basic mathematical arithmetic operations, plus, minus, multiplication, and divide. Use the asterisk for multiplication and / for division. Exponentiation, or raising to a power, is done with the caret. For complicated expressions or grouping, use parentheses. Note that multiplication is not implicit like on some calculators or how you might write it down mathematically. You have to explicitly include the asterisk, in this case between the 3 and the parentheses. At any time to clear the command window, this does not clear the variable space. Use clear, CLEAR, to do that. But clearing the command window, you can clear the command window with just CLC. There is an enormous number of built-in functions, and then you can have an extended set of functions using actually packages, also known as toolkits in MATLAB. But for this course, we'll essentially just be using the built-in the built-in functions, and won't require any additional packages. But all the standard mathematical functions, the trigonometric functions. There are various rounding functions, which will round to the nearest integer. Floor truncates, rounds toward 0. Ceiling actually rounds toward the next integer above. There are operations for working with complex values, for finding the angle of a complex number, or the radius or absolute value of a complex number. Uh, I'm going to skip this exercise. You can continue with this as you want. Actually, well, let's look at this one. You can pause the video, read this slide, see if you can carry this out and do these operations. Okay, so pause the video at this point. Okay, so the script would look something like this. Actually, let me show it to you in the Octave window. Here, first I compute the number of seconds in a day. Now, you want to come up with some standard convention for naming variables. In the lecture slides, he's using a convention known as camel case, where the variable starts with a lowercase letter, and then subsequent words that make up the variable name. I'll start with capital letters and use good variable names. This can help tremendously when you're debugging, calling seconds per day. This is the number of seconds in a minute times the number of seconds in an hour times the number of hours in a day. Using a variable name like seconds per day is much more descriptive here than calling it X. I don't even need to really add a comment line indicating what this is. And then we compute the time constant that was mentioned, and the number of class days is just, we take advantage of the number of seconds per day. The knowledge at the end, we use our exponential function. It's exp minus end of class over tau. Then I use the display function. And here again, I'm using the string concatenation feature to concatenate, in this case, 3 strings. At the end of Engr390, I will know, and then we can convert a number to a string. Numbers and strings are different, okay? But I can convert a number to a string using the num to string function. This actually returns a string. Again, at the command line, when I use this, I get back actually a string. It looks just like the number, but one of the things I can do, is actually num to string 100 will give me back, a complete string, But if I try this with just the number, I'll get an error because I'm trying to concatenate a number and a string. Actually, here it gave me the ASCII representation, or I think maybe actually even the binary representation there, but it didn't give me the result that I wanted. But again, num to string will convert a number to its ASCII text string equivalent. Okay. Transpose, just use the apostrophe to transpose. Actually, it works differently on complex matrices versus real matrices. If for real matrices, there's actually no difference between the apostrophe and then a period apostrophe. They both do the same thing. On complex matrices, the apostrophe actually transposes and takes the complex conjugate of all numbers. On complex matrices, dot apostrophe gives just the transpose. The complex conjugate transpose tends to be a more common operation for when working with complex matrices. But here we've defined A as it's a mix of real and complex numbers, so the entire matrix will actually be complex. For addition and subtraction, you have to make sure that the corresponding matrices or vectors are compatible for addition and subtraction. That means they actually have to be the same dimension. So you'd get an error if you were trying to add a row vector and a column vector. Let's say the row vector is 3 rows by 1 column. The column vector, I'm sorry, the row vector is 1 row by 3 columns, and the column vector maybe is 10 rows by 1 column. Those aren't compatible for addition. Here they're showing a row vector with 4 elements and a column vector with 4 elements. Of course, you could transpose the row vector into a column and add them, or transpose the column vector into a row vector and add them, and you get a row vector as a result. Be aware that a lot of the operations, the sum operation on a row vector will give the sum of all the elements. So let me actually just generate a random row vector here, 1 by 5 columns, and I get the sum of the row that will just add up all the elements in the vector, or correspondingly the product. Okay, but if I generate a random 3 by 4 matrix, what the sum will do on M is add up the columns. Okay, similarly, the product will add up all of the columns. So one of the ways we could get, if you really want the sum of all the elements, I could actually do the sum of the sum. This would then add up all the columns and then add up the elements in the corresponding row vector. And correspondingly, I could do something like this using product. We'll talk a little bit more about this when we get into indexing matrices. There's another way to do this, which I actually prefer. Okay. Be aware that a lot of the mathematical functions that work on scalars also work on vectors. They work on them in most cases. They'll apply the corresponding function to each element in the vector. One common source of confusion, though, is that the mathematical operators of multiplication and division and exponentiation actually have 2 modes of operation, element-wise and then the standard matrix corresponding operation. In this course, you actually will use both modes, and it can be a little bit of confusing. To do element-wise operations, to add all of the elements in one matrix to all of the elements in another matrix, or rather multiply them. Matrix addition does that automatically, but to multiply all the elements in one matrix by all the elements in another, use dot asterisk instead of asterisk. A regular asterisk tries to do a matrix multiplication. A regular division actually would multiply the matrix on the left by the inverse of the matrix on the right. But if you use dot slash, it will divide every element. So here are a couple of examples. Here, when you're using the dot elements, the two matrices have to be exactly the same size. It wants to multiply each element by the corresponding element in the other matrix. So here they're not compatible for element by element multiplication. They are compatible. This is a 1 by 3 vector times a 3 by 1 vector. So this would work without the dot. It's going to actually give you just a scalar. 1 by 3 times a 3 by 1 would give you a 1 by 1 matrix result. But with the dot element, it gives an error. So here we actually, it's taking the product. It's not doing a matrix multiplication. It's taking the product of every element times every element. And here's the same for 3 by 3 matrix. Here we could use either the dot operation or the standard matrix multiplication. We'd get a much different result, and you should try this to verify that. Here we're getting the product of multiplying every element in the first matrix by every element in the second matrix. We're not getting actually the matrix multiplication. And the same's true with, here we could either square this matrix, which would be this matrix times itself, if you use just the caret operation. But with the dot caret, it actually raises every element to the corresponding power. So, for the most part, in the statistics where we're working with data sets, we often use the dot operators and do element-wise operations. But in the linear algebra course, we almost do all matrix operations, and so use the operations without using this standard operators without the dots. So again, we use both, are very useful in different applications. And multiplication can be done in the standard way or element-wise. Here, this is showing the matrix multiplication. This is showing the squaring a matrix, multiplying by itself. Again, this would give an error with a dot operation. This would work fine with a dot operation. This would work with a dot operation as well, but give a different result. Here we're doing the matrix multiplication of these two matrices. I'm not going to have you do this exercise. I'm not going to do it. Actually, I've deleted, I think, the file that held the start variable. If you still have that, you can work through this. Here are the corresponding commands to carry out this operation. So you could pause the video at this point to extend that hello world. I'm going to proceed. Again, this is just a continuation of that exercise where you're actually going to compute now what do they have you doing? How many seconds since the start of class? So we have to read in the start variable and get the current time by subtracting the current time using the clock from start, and then display that. But as I said, I've deleted that file, so you can do this if you want, but I'm going to go ahead. You can, and I've already used some of these. These are pretty handy for getting initial vectors of all ones or zeros or a random vector or matrix. So it's handy if you want to test out some operation. Again, these are often used to initialize variables to the appropriate size. For example, I can't just, if I don't have a variable z, I can't just get the 10th element. I'll get an error. But if I initialize it, zeros 1 to 30, and then z of 10, then we'll get the 0th value. Or it's another operation that's, if I want a random, I've done this quite frequently. 3 by 4, and I'll leave off the semicolon here so we can see it, just to test various operations. Another way, a couple different ways to generate linear vectors are available. Probably the easiest way is to actually do a start colon, and then the final value. So this will generate a row vector with elements 1 through 20. Again, an easy way to generate a column vector is just transpose that row vector. I can actually do, minus 10 to 20 here. Let me actually give that as a row vector. Okay, so an arbitrary starting value. I can even specify an increment. So this will go from minus 10 to 20, and elements by increments of 2, minus 10, then adding 2 until we get all the way to 20 here. So the other way to do that, or another way to do that, is to use the linspace function, where you give it a starting value, minus 10 and 20. And then in this case, I think there are 16 different increments. This will give me exactly the same vector. I often use linspace, when we're plotting functions and we want maybe 500 points between minus 5 and 5. Again, we don't have to use integer values. I can go from 1 to 2 in 0.1 increments. So 1, 1.1, 1.2. So this colon notation is quite handy and quite useful. Okay. There is a log space function to generate logarithmically spaced data. Let's see, again, you can go through this exercise if you want, using, here we're going to generate a vector of 10,000 points. That TVEC would have 10,000 points between 0 and then the number of seconds in 5 days of class. And then here's the corresponding knowledge vector, which would go from 0 up to almost 1 here over the length of time. We can pull out individual elements in a matrix. Here, as this example shows, we can generate this matrix. This is a row vector. Element indexing starts with 1, not 0, as it does in some programming languages. For example, in C and C++, the first array index is 0, not 1, so that causes a bit of confusion if you're coming from another programming language. But this is more natural when we're dealing with matrices. Our first index is 1. And then here's some alternate, notation. Here we're forming the x vector. This is going to give us the elements in x with indices between 2 and 3. So this would, give us a new vector consisting of these two elements. There's a special operator we can do from 1 to n would give us all the elements from a new row vector with all the elements out of x. Here, making n minus 1, we're just going to get 12, 13, and 5. Okay. For matrices, there's two ways to index them, either using subscripts, which is kind of natural from our linear algebra notation. So the first index would be the 1, 1 element, first row, first column. This would be the 2, 1 element. This would be the 2, 2 element. The alternate notation treats the matrix as one long array with the columns stacked on top of each other. So this would be the first element, second element, third element, fourth element. So you can use either of these notations, and they both come in handy. So let me actually just generate a random 3x4 matrix. And I recommend that you do this, and so you can play around with these. This will give me the second and third rows and the first and second columns. So this would pull out this portion, second and third rows, first and second columns out of this matrix. So I can use notation like this to pull out a submatrix. Now notice I haven't saved this. I've just used this and assigned it to answer. I could assign it to another variable. Now this doesn't modify the original matrix. It's still the same. Or I can, if I use just a single index, it's going to treat this matrix as one long vector stacked by columns. So the fifth element would be this 0.4125. This is called using an index, addressing it by index. That's also the second row, the second column would pull out the same number. One common notation is to do this, which will convert any matrix into its corresponding vector representation. Again, where it's stacked column by column. Again, this is a little bit different than the way C and many other program languages store matrices. They store them by rows, but in Octave and MATLAB, they're actually stored by columns. And so, I can easily convert a matrix into a vector. This is handy, for example, if I wanted to find the maximum value in a matrix, the max function actually finds, by default, finds the maximum in each row. But if I instead use m colon, oops, mistyped that, this will find the maximum in the entire matrix because it converts the matrix to a column vector and passes that to max, and then max will find then the maximum element in that entire matrix. So it's a handy notation. Equivalently, I could do 1 to n. That's what the single colon represents. So both ways come in handy. You can pull out arbitrary rows, match with arbitrary columns here to pull out corresponding submatrices. A single colon represents all columns or all rows. So this would give me the first row and all columns. So this would give me a corresponding 12 and 5. This would be all rows in the second column, so this would be 5 and 13. This would actually return would return a column vector. The first one would return a row vector, or the second row, all columns. I can actually replace here. I'm assigning to, this is on the left side, so I could replace the entire row here. The dimensions have to match. This has to be a row vector with the right number of elements. Okay. There are, functions to find the minimum maximum value of a vector. Okay. Let me actually copy this and over into MATLAB or Octave. So we've got that. Now, again, max on the vector, we'll find the maximum in the vector. If MATLAB supports multiple return arguments, so if you look in the online help, it will, by default, it returns just the maximum value. With two return arguments, it returns the maximum value and the corresponding index in the vector. So, vec of I here is that maximum value. So it's returning not only the maximum value, but the index in the vector where that maximum value occurs. So, a lot of the functions will do that, may have multiple return values. Again, help will completely describe, here what the return values are, either just the maximum or the maximum value and the index. You can also use the find function to get just the index if you want, or multiple indices. So let me actually copy and paste this. So here's our vector. This will return the indices of all the elements in the vector that are actually between 2 and 6. Now, again, that's at index 1, which is 5, and index 2, which is 3. Those are the only two elements here that are within that range. If I wanted to pull, I can use this new vector now to pull those elements out, the elements that are within that range. So we'll look at find a little later on. But so I'll try to use this notation. Subscripts are, we have multiple subscripts to pull elements or submatrices out of matrices. An index treats that corresponding matrix as a long column vector, and it's just a single number. And it seems a little strange that we have support for both ways, but sometimes we can simplify operations by treating a matrix as a long vector. Again, I'm going to skip this exercise. You can go through this. These slides are available, so if you want to go through this. Okay, this completes this lecture. I'll have just a brief one final lecture on plotting when we continue.